there, Algebra 2. Welcome back. This is the lecture associated with Thursday, March 19th. I hope everybody's doing well and taking care of themselves and everybody they love. Today we're moving forward with some stuff about factoring. And, you know, if I were in the classroom, I know I'd be getting lots of ribbing about this because I've said many times factoring is one of my least favorite things about algebra. But we're gonna take this on, and by the end of this period, I'm gonna like it. Now, you should have a copy of a handout that I've posted for you on Google Classroom. It's called Factoring Special Products Handout. You can print that. I would recommend printing it and having it with you. You could be taking notes on it. At least have it up as you're working on this stuff. Alright, so what we're going to be doing is we're going to be doing some factoring today. That's, you know, there's going to be some patterns to it. And particularly, we're going to be working with trinomials. Remember, trinomials are the type of polynomials that had 3 terms in them. And we're going to try to get as many of them as possible to be what we call perfect squares. Now, that term, perfect squares, let's be sure that we're clear about that. I mean, I think we have no trouble understanding what we mean by perfect square if I'm talking about, like, a number, like 25. 25 is clearly a perfect square because it works out so nicely to just 5 squared. You know, the square root of 25 is 5. But 26 is definitely not a perfect square. I mean, the square root of this is something horrible and irrational and not such a good thing to work with. But we're not working just straight with integers like this. Rather, when we're talking about perfect squares here, we're talking about asking if a question like, if an expression like that is a perfect square. Is there a way to factor it so that this expression is a little binomial, that this is a trinomial, can we get it to some binomial, and it's in fact going to be this, squared. You can use FOIL and figure out that I did that right. In fact, we're going to do exactly that problem in just a few minutes. Alright, so that means that this is an example of a perfect square. There's some number, there's some expression we could write squared that gives us this trinomial. Alright. These ones that are trinomials that are just an x squared and an x and then a constant term are not actually going to be that bad. Let's do those guys first. And I have a little bulleted list of steps there on the first page of the handout here. First off, we want to look at the leading coefficient of the original polynomial. In this case, there's sort of a hidden 1 right here. And we ask ourselves about this leading coefficient. And we ask, is that a perfect square? Yes. In that case, oh, and it has to also be positive. Oh, is it positive and a perfect square? Well, then great. All right, we're in good shape on that. Our second thing that we need to test is the constant term. It needs to be positive and it needs to be a perfect square too. In this case, yeah, 9 is 3 squared, so we're in good shape. We kind of passed that second bulleted test right there. And then the third test is a little bit more complicated. We want to look at this coefficient of just the middle term here, and we want to ask ourselves, is that 2 times the square root of, I'll just write leading coefficient, times the square root of the constant term. So in this case, is it 2 times the square root of 1 times the square root of 9, which is 6? And the answer in this case is yes, it is. In fact, it's got a negative sign in front of it, but we'll deal with that in just a little bit. In that case, then, we have passed all the 3 bulleted points there on the middle of page 1, and therefore we think that this polynomial can be factored. I'm going to close this door here because my kids are being wild down there. Hopefully that will reduce the noise. I'm up in the guest bedroom and my children are doing something God knows what downstairs. Alright, so let's actually try to factor this. This is going to be the first example on the handout here. We already know, because we passed all these tests, that it's going to be possible. Alright, so in this case, it's going to be the square root of this term, the square root of the last term, and the sine of the middle term. This is a perfect square of this expression right here. We could always check this using FOIL if we really wanted to. No, I shouldn't say if we really wanted to. It's a good habit to be in. Is this work out? The firsts times the outers, plus the outers, plus the inners, plus the lasts. X squared minus 6x plus 9. And it works out. Get rid of this 1 now up here. And we're happy. And that factoring wasn't too bad. Notice that I got this sign from the sign of the middle term of the trinomial here. All right. You've probably been doing this kind of factoring of little terms for a while now. You probably did it to a greater extent in Algebra 1 than we're going to do it now. But the book, I got some of this stuff in the book, I got some of this stuff from Discovery Education, and they want you to notice sort of the pattern here. What you really want to do is see if you can take your expression. Here, I'm going to do example 1, the next example on the second page of the handout. Let's actually do this expression right here. 16x squared plus 24x plus 9. And what the book and the website all want you to do is realize you could write this term here as 4x, the quantity squared, plus, we'll write this right now as 24x, plus this quantity here would be 3 squared. We'll call this A, and we'll call this B, and A and B are related to this middle term as being 2AB. In other words, if you can come up with some A and some B so that this original expression can actually be written as A squared plus 2AB, well, I guess they're actually, here, let's see here. In my original handout, I was doing it here, let me fix this here. We're going to eventually do it the way I just showed right now. I got a little out of order of the steps here. What if we made this 4 squared times x squared plus 24x plus 3 squared? So this could be called A equals 4, and this could be called B, and we'll call it B equals 3. So then we have A squared x squared plus, we'll come back to something else, plus B squared. Now we got this middle term right here. And that middle term is 2abx. If this works, let's double check. Is the first term a equals 4, so 4 squared times x squared is 16x squared. Good. Is this last term 3 squared? Yes, it's 9. Is this middle term 2 times 4 times 3 is 24? Yes, it is. Okay. If that's true, then the factors are just ax plus b squared. So since a was 4 and b was 3, that's our answer. And we got this plus sign because this term here was positive. If it had been negative, we'd have used a negative sign there. We'll do an example like that in just a minute here. So this expression up here can be factored as a perfect square like this. Let's do another example of this technique here for a second. Let's clear this out and look at the example on page 2 that's right below that. That's the second example on page 2. What if we had this expression here, 25x squared plus minus 20x, yes, let's use that, minus 20x plus 4. Well, this 25 is a square. I mean, we could call that a equals 5, and then this is a squared x squared. That 4 is a perfect square. We could call that 2 squared. And this term over here at the beginning here is minus 2 times a times bx. All right, it works. We are able to make the pattern work. So the factorization of it will be ax minus b. I got a minus because the middle term has a negative sign there. And this will be 5x minus 2 squared. This takes a little practice to get these guys right. Now remember, not every polynomial can be factored in this way. Plenty of polynomials can be factored in some way, can't be factored in this way. Like they won't necessarily end up as a perfect square. In fact, that happens in that that last example on page 2 of your handout here. Let's take a look at that one real quick. We're working with 3x squared plus 8x minus 4. All right, is this a perfect square here as the leading coefficient? No. I mean, I guess we could maybe take a big pass here and say, well, maybe a is the square root of 3, maybe. But b, remember, we wanted the constant term has to be positive. I mean, what kind of b am I going to come up with that b squared is -4? Well, I mean, I guess it could be like 2i or something like that, but then we're not even talking about real solutions. So this guy's not going to have no perfect square factorization. Doesn't mean it can't be factorable. I have to admit, factorization. I have to admit I didn't actually check to see if this can be factored any other way. It's very possible that this is like 3x plus 1 times 1x plus 4 or something. I don't know. I haven't actually tried it. It's very possible, but it cannot be factored as a perfect square. Let's try to expand that idea we had of using a's and b's to substitute. Is actually what I was doing before, and I kind of got turned around here. We're going to make it. We're going to expand our idea about these trinomial terms to have ones that have both x's and y's in it. Like I worked through an example here at the bottom of page 2 where it's 4x squared plus 4xy plus y squared. And what the book is telling you to do is check this test that we have on the top of page 3. There'll be a couple of things we can check, and if we can pass all of the tests that are at the top of page 3, we'll be able to do this as a perfect square factorization. Alright, so the first thing we ask ourselves, is the first term positive? Is the leading coefficient positive? Sure. Can that whole first term be written as a perfect square? Sure, this could be written as 2x, the quantity squared. Because that would be 2 times 2 times x, which is 4x squared. So we could make some a that is 2x, and this first term could be written as a squared. Alright. How about the last term? Is the last, no, on the second bulleted point there at the top of page 3, is the last term, that constant term, is it positive? Sure, it's got a positive sign in front of it. Can it be written as some quantity b squared? Yeah, I mean, this could be b equals y, and then this could be written as b squared. Alright, so yes, we're good with that one. Now that I have an a and a b, is that middle term 2ab? Is it 2 times a, which is 2x, times b, which is y? Is it 4xy? It is. Now, it could be plus or minus. We're going to get to that in just a second here. But so we have passed all of the tests there at the top of the page there. This thing is factorable as a perfect square. And when it comes to it, it's going to be a, it's either going to be plus or minus b, the quantity squared. Because this term is positive, it's a plus. So we can factor this as a plus b, the quantity squared. And we just substitute back in what did we call a? 2x. What did we call b? Y squared. So this quantity right here can be factored like this. And again, I always recommend using FOIL and making sure that this is correct. Let's check our work here. Is 2x plus y times 2x plus y what we were looking for? That'll be 4x squared plus 2xy plus 2xy is 4xy plus y squared. And that does match the original equation, so this worked out. Cool. Whew. These things can be quite the mess here. I actually did a couple examples right there in the handout. I'm not sure we'll do all 3 of these, just because it gets a bit tedious to sit there and do them all one by one on the board while you're watching YouTube video. So let's try some of them. How about the top one on page, the example about a third of the way down the page on page 3 of your handout. It wants to know if we can factor 4x squared plus 12xy plus 9y squared. Can that be factored as a perfect square? Alright, so we got a couple of tests we got to pass. We got to pass that bulleted list of tests at the top of page 3. Is the first term positive? Yep. Can it be written as a perfect square? Yes, that first term could be 2x, the quantity squared. So a is apparently equal to 2x. So that we could be writing that first term as a squared. Now we look at the back term. Is it positive? Yes. Can it be written as a perfect square? Sure. This could be 3y, the quantity squared. Then b would be 3y. And that term would be b squared. That would be a perfectly good way to write it. Then, is that middle term 2ab? Well, let's see. That would be 2 times 2x times 3y. Let's see, that'd be 4, that'd be 12xy. And that is what we have. So, we're good. We have passed all 3 of the tests at the top of page 3. So it's going to be a something b squared, and that something is either a plus or minus depending on the sign of the middle term, and it's a plus. So we just substituted what we meant for a and b. A is 2x, b was 3y squared. And again, I strongly advise you to actually check that with FOIL and make sure that it does give you what you need back up here. I can tell you on this one I did check it and it should be fine. Cool. Let's factor another one. Let's do the second example, the one right below this on page 3. All right. The second example, how about 64x squared minus 32xy plus 4y squared. And the question is asking, can we factor this as a perfect square? And if so, do it. Again, even if we can't make it as a perfect square, it's probably could be factorable, but that's not what we're learning today, okay? It's very possible that this could be factored some other way. But now we're going to use those 3 tests at the top of page 3 and see if we can factor this. First thing, is the first term positive? Yes. Can it be written as some quantity a squared? Sure, this could be 8. This could be 8x squared. So a is 8x, and that term becomes a squared. Okay. We turn now to the constant term. Well, not the constant term, the third term of the polynomial here. Could that be written as some kind of square? Sure. It could be 2y, the quantity squared. In which case, then b is 2y, and that term is b squared. Now we turn our attention to the middle term. Is it 2ab? 2 times 8x times 2y. Let's see, that'll be 32xy. Yeah, now it's got a negative sign in front of it, but it matches. So our term, our factorization will be a something b, and it'll be minus, because the middle term was a minus. So it is 8x minus 2y, the quantity squared. And definitely, again, I would strongly recommend checking those things with FOIL, but I already did check it with FOIL, and it's good. Whew. Just drawing your attention to the third example on that page here. That one, it turned out it didn't work. Let me write out down what the problem there was. We don't actually need to go through all of it because there's so much to go through, actually. That problem was 64x squared minus 32xy minus y squared. And it'd be tempting to go through the same process, but it's not going to end up working. It's pretty hard to figure out what kind of value of b could become negative y squared. I mean, probably something like I times y would work, but then we wouldn't even be talking about real numbers anymore. So this one does not have a way to make it a perfect square factorization. Again, I didn't actually try it. A lot of times these have other ways they can be factored, but we're working on perfect square factorizations here. This idea of trying to take the first term and rewrite it as a squared, and then just figure out what that a would be, and that last term and rewriting it as b squared is super powerful. And in fact, lets us do some problems where the degree of the polynomial that we're trying to factor is higher than 2. And I really like the problem, it's not the bottom problem, it's the second problem from the bottom on the page there, where it says, can we factor x to the 4th plus 2x squared y squared plus y to the 4th? Can we do that? Alright, well, we just got to work our way through our rules here. Is the first term positive? Yes. Is it a perfect square? Sure, we could write this as x squared squared, where a was equal to x squared. X squared squared is to the 4th power. How about the back term here? Y to the 4th? Well, that's not some big shock. It's going to be y squared squared, so our b is going to be equal to y squared. That's a squared. Alright, now let's check the middle term. Is the middle term 2ab? So it'd be 2 times x squared times y squared. Well, in fact, that's exactly what it is. Therefore, we can say that it's going to be a something b squared, where that something will be this sign, so it's plus. And as a consequence, this will be x squared plus y squared, the quantity squared. Maybe I better check that one by FOIL to make sure I know. X squared plus y squared times x squared plus y squared. firsts, outers, x squared plus y, I'm sorry, x squared times y squared, plus another x squared plus y squared is 2x squared y squared, plus the lasts. And it did check out. It matches the original problem. All right. Whew. Well, that's kind of cool. I mean, you might be tempted to think something could even be done with this to factor it any better than that, but we're not going to do anything better than that right now. Huh. Let's do a very similar problem and see if we can make it work. In fact, I'm not going to erase this whole thing here. What if this had been 2xy, I'm sorry, let's go here. What if there'd been like the bottom problem is right there, where it's x to the 4th power plus 2x squared y plus y squared. All right, can we make this one work? Well, is this term positive? Yes. Can it be written as a square? Sure, it can be x squared squared. So a is apparently x squared, so that this term is a squared. So far, so good. Turning our attention now to the last term. Can y squared be written as a square? Sure. If b was just equal to y, this would be b squared. So far, we're in business. How about that middle term? Can that be written as 2ab? Well, that would be 2 times our a times our b, and in fact, that's exactly what we have here. Congratulations, we passed all the tests, which means that we can factor it in the form a something b squared, and that something is the sign of this. So we just plug things in. Our a was x squared, and our b was y. And this is the factorization of this. And again, we could actually sit down and do it all carefully by, check it all by FOIL, but right now we're not going to do that here. There's one more example there near the top of page, what are we on here, 4, I guess, of the handout, but I don't think we need to work through all of them. You can do some of them yourself, and of course, always feel free to contact me via text or via email. I love answering questions, okay? Now, you know, neither Discovery Education nor the OpenStax textbook is going to be willing to leave well enough alone with this, right? They're obviously going to want to take this a little bit further. And one thing that we can do with this that could be taking a little bit further is sometimes we can't quite get it into the form of a perfect square until we factor something else out first. When there is some common factor in all of the terms going into the equation that we first need to factor out. That's hard to put into words. Let's do that as an example first. Let's do the first example. Okay, so on page 4, it's this one right up here, about a third of the way down. It's asking us to factor this expression. 4x squared y plus 8xy plus 4y. Well, when you tackle this guy here, if you start with our rules about trying to figure out how to do a perfect square factorization, it's just going to be a mess. You're not going to get anywhere with it. But I'm noticing that there's a 4y hidden in each of these terms here. Let's factor him out. That's called the greatest common factor. We're taking that all out, leaving behind just the x squared, leaving behind just a 2x, and leaving behind just a 1. Oh, well, now that I factored this little piece of garbage out, the greatest common factor, the piece that's left here sure looks like it's a perfect square. In fact, with a little bit of fussing, you can see that it is x plus 1 squared. Right? Our first term is positive, it can be written as a perfect square. Our last term is positive, it can be written as a perfect square. This term is that a plus, I'm sorry, 2ab. We're in good shape. We're in good shape here. And so that's our factorization there. Cool. All right. Let's do the one right below it while we're at it too. I wish we were in the classroom. We could have people come up to the board and show me how fast they can do them. I mean, like on the next problem there, we have x to the 5th power, y, plus 2x to the 3rd power, y squared, plus xy to the 3rd power. Well, feel free to use our perfect square rules on this to your heart's content. You're not getting anywhere with it, okay? This is just not going to factor that way. But I am noticing that they all have at least one x in them, and they all have at least one y in them. I can factor out the x, y, leaving behind x to the 4th plus 2x squared y plus y squared. Okay? Now I'm wondering if this term that's in the square brackets here, maybe it could be a perfect square. I mean, this term right here, is it positive? Yes. Can it be written as some number squared? Sure, it could be x squared squared. So a is x squared. Turning our attention to the last term, is it positive? It is. Could it be written as a square? Sure, if b was equal to y, then this is just b squared. Great. Is this middle term 2ab? Is it 2ab? Let's see, is it 2 times a is x squared and b was y? 2a? Yeah! So this is going to be that big middle term that was originally in square brackets there, can be written as a plus b, the quantity squared, which, substituting back in, a was x squared and b was y. And we did it. And again, I would strongly recommend when you're doing this on homework or something like that, then to actually use FOIL and make sure that this works. Whew! Those guys get messy fast. I'm starting to get a little bit stressed out about factoring. But then the book kindly sends us in a direction of something that's a little bit more familiar. It's actually an Algebra 1 thing. That just doesn't necessarily mean that you remember it right off the top of your head. That is the difference between two squares. I mean, if I have two terms like x squared minus y squared, they're both squares and they're just subtracted from each other. Your difference of two squares rule tells us that that factorization will be x minus y, x plus y. There's no square. Again, you can feel free to use FOIL and make sure x squared minus, plus xy minus xy minus y squared. It'll work out. This is your basic difference between two squares rule. Odds are you did this to death in like 8th grade math or something like that. So like for example, here let's make it a little bit more complicated. What if we did 4x squared minus y squared? Can this term be written as some kind of a squared term? Sure, it could be 2x, the quantity squared, where a is equal to 2x. And this back term here, it is a nice square already. B is equal to y. So it's going to be something like a minus b times a plus b. And just do the substitution back in. 2x minus b, 2x plus the b term. Well, there we go. And we did it. Those you've probably done before in like 8th grade math or Algebra 1 or something like that. So I think we've got that under control. Boy, I really hate the next example there. In fact, I almost thought about not showing it to you, but then I thought, you know, I'm such a coward about factoring. I feel like I should at least show you this problem here. This is, I think, pushing it a little far in my opinion. But they're asking x squared minus 6x plus 9 minus y squared. And I'll be perfectly honest with you here. If that was something that just came across my desk and said factor it, I'm not sure I would remember this trick. Okay? So this is not something that I see every day. But what they want you to notice is if I put some parentheses around this term right here, this term that has the square brackets around it, that term itself is a nice perfect square. This term is positive. It can be factored to be a equals x, and then this is a squared. This term right here, b could be equal to 3. This term in the middle is that 2 times a, which is x, times b, which is 3. Yes. So this middle term that was in square brackets here could be written as a minus b squared. It could be written as a minus b squared minus y squared. All right. If you got that far, I'd be happy and impressed. But then they said, notice, this is a square, this is a difference, and this is a square. So once again, your difference of two squares rule should work. I mean, let's call this, for the sake of argument, this is big A and this is big B. Then this term is a squared minus b squared, which means this is a minus b times a plus b, which would be, let's put the a back in there, minus b, a plus b. All right. This stresses me out. This is the kind of thing in factoring that makes me think it's a little too far. All right? There'll probably be some of these on the homework. I haven't made the homework yet, but we'll get there. All right. Finally, on page 5 of the handout, they step one little step further and start talking about perfect cubes. Well, perfect cube might be a different one. Let's say the sum and difference of two cubes. If you have a term that you are supposed to factor and it's something like x cubed plus y cubed. Where this term here is a perfect cube. I mean, we could have like a equals x, and this term would then be written as a cubed. And this term over here could be written as b is equal to y, and then this is b cubed. This is a sum of two cubes. And actually, they provide you with how to factor a sum of two cubes. Now, wait a minute, where did I go with that here? Yeah, it's on the last page right there. The sum of two cubes, right about the middle of the page right there, is, so if you've got like a cubed plus b cubed, there's a factorization of it. It's a plus b times a squared minus ab plus b squared, and then you just plug everything back in. A was equal to x, b was equal to y, a was equal to x, b was equal to y, like that, just plugging everything back in, and that would be your answer. This is a perfectly good factorization of a cubed plus b cubed. Now, on Discovery Education, they actually had an amazing way of showing that this is true. And it was a very hands-on thing, working with blocks and so on. And it's super neat and totally not the kind of thing we can do via distance learning. I mean, it was a very hands-on thing. If we were in a classroom, we would do it. But it's actually pretty cool. Here's the deal. See those rules in the middle of the last page of the handout? I would definitely say that those should be in your notes or whatever, because those are hard to memorize. It's easy to make mistakes about the signs of those things and so on, and they're pretty useful. I mean, look at these problems that we have down there at the bottom of the page right there. How about the next one? It says factor 8x cubed plus y cubed. All right, can we get this into that a form where could this be written as like for example 2x, then a cubed would be 2x cubed, which would be 8x. So hey, this worked out. We got this one here. And over here, this one's easy. B is just equal to y, so b cubed is just y cubed. We got this one right here. This is clearly a sum of two perfect cubes. All right, so then that means that the first, yeah, this perfect cube plus this perfect cube is equal to, let's see, at the top of the two rules right there, it'll be a plus b, where a is 2x and b is equal to y, times a squared, which is 4x squared, a is 2x, so a squared is 4x squared, minus ab minus 2xy, all right, times b, plus b squared. B was just equal to y. All right, and that's a perfectly good factorization of this. That's really cool. And that's all the farther you have to take these things. Yes, once in a blue moon, this thing can actually be factored too, although that doesn't happen very often. Most of the time, that's the end of the road for that. I do want to show you the last problem on this handout because it kind of combines a bunch of the techniques that we have learned today into one big ugly problem. It tells you to factor this ugly expression. 6x cubed y plus 48x, I'm sorry, no, 48y squared. No, y to the fourth power. Sorry, it was a big mess there. 6x cubed 48, 4x cubed y, yeah, okay, there we go. What I'm noticing is each of the two terms here has at least a y in it, and each of the two terms in there can be divided by 6. In other words, we could factor 6y out right at the beginning. That's our greatest common factor, leaving behind x cubed plus 8y cubed. Alright, now like a shark, we smell blood in the water. This looks to me like a sum of two cubes problem. If that's a sum of two cubes problem, a is apparently equal to x, so that a cubed is x cubed. And b in this case is equal to 2y, so that b cubed is 8y cubed. And so then we can write out these factors here. It's going to be that top rule there of the two rules on page 5 there. It's going to be the top one, a plus b, so x plus 2y times, and then the second half there, a squared, a was x, so it's x squared, minus ab, minus ab, that's 2x times y, yep, and then times the b term squared, so that'll be 4y squared. Whew, boy, is that what I got for that problem right there? Boom, 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 boom. Yeah, that's great. And again, smart, wise students will check those kind of things with FOIL before they hit submit, but it'll work. All right. That seems like a lot of factoring for one day. I gotta say, preparing for this lecture was a lot of work. I don't love factoring. All right. This is going to be an assignment that I'm going to post for you on Google Classroom. It will actually be a Google Forms type page to fill out, but you'll probably be doing the homework on paper and then just entering your answers there. I don't need to see your papers. On the other hand, if there's things you want me to see on your papers, then just send them to me, take pictures of them or whatever. I'll just keep them on file. Yeah, I think that's everything. I'll post whatever this is. I have it here. It's section 6.3 of the OpenStax textbook that gives more explanations. If you don't, I know some of the students wanted to have a book. So the OpenStax section 6.3 has different explanations than mine and different examples than I gave and so on. All right, you have a fairly long period of time until this is due. I think officially this is due like Thursday, April 9th or something like that. I'll have the right date though posted on Google Classroom. All right, I think that's everything that we need, and I appreciate your time with this, and good luck with all this factoring.